In example 1, we're asked to analyze the following function. We've got f of x here. Looks to be a rational equation. So one of the things that we can do right away is we can see what would help us to graph this thing. If we take a look at our asymptotes, we'll do maybe some vertical asymptotes over here on the right hand side, or we'll be investigating holes here as well. What we like to do is we'd like to take 3x squared minus 27, and we would like to divide that by x plus 3. So if possible, we're going to try to factor the numerator. The denominator is already factored. So we could pull out a 3, that'd be x squared minus 9 over x plus 3. And this is the same as 3 times x plus 3, x minus 3. Hopefully you can see that here on the side. I'll move that over a little bit for you. X minus 3 over x plus 3. A value of negative 3 here will make the denominator 0. We got to figure out if it's a vertical asymptote or a hole. We look in the top, we see a factor of x plus 3. So this one's definitely going to be a hole at x is equal to negative 3. And you can even see here that we have a spot on our functional analysis chart for points of discontinuity, so we could put x is equal to negative 3. For this one, there won't be any other values that cause the function to have division by 0 or to not exist, be undefined, and so we won't have any vertical asymptote. We can look at the horizontal asymptote though, and this one is going to be, let's see, we've got 3x squared, so this is for our horizontal asymptote, or HA I guess I could say. And in the denominator we don't have something square like x squared, so we need to add a filler in there. And you can see pretty quickly here that we get division by 0, so there won't be any asymptotes either. This graph, we could find a slant asymptote. The slant asymptote would occur when we took x plus 3 and divided it by 3x squared minus 27. If we look at our work on the right hand side of the board, you can see that we would divide these out, and that would be the division part, and we'd be left with 3x minus 3, or 3 times in parentheses x minus 3, which is 3x minus 9. So if we really wanted to, we could write here that there's a slant asymptote at 3x minus 9, and we'll do y equals, because that would be an equation of a line. I'm not going to draw that, as you're going to see here, because if I do, it's going to get a little confusing. This graph, I'm thinking, is going to lie right on that line, but we'll see what happens. The next thing we can do is find any x-intercept or y-intercept. So remember, to find an x-intercept, just set the numerator equal to 0. So for this one, we can do 3x squared is equal to 27 if we added 27 on each side up there. Divide by 3, we've got x squared to be 9, and x could be both positive and negative 3. Remember though, there's a point of discontinuity here at negative 3, so the only value that works here would be positive 3. So we could do 3 comma 0 as our x-intercept. If we graph this, it's okay at this point to go ahead and start graphing that. We got to remember this negative 3 value though. For x, we got to leave a space there. It's a point discontinuity. We got to leave a hole there. But we can put 3 comma 0 in for sure. So there's that point. As far as the y-intercepts go, what we can do is we can just take a look at the constants. If we substitute 0 in for x, we're going to have negative 27 over 3. So we're going to have a point, 0, comma, this value right here, which is negative 9. So at 0, negative 9, we should have the y-intercept. At this point, we could probably do the domain and range, but I like to graph it first, and then we can also do the end behavior quite easily if we look at it graphically. So if we enter this one in y sub 1, use parentheses around the numerator position, 3x squared minus 27, and then in the bottom we need to use parentheses as well, and that's going to be x plus 3. So hopefully you can see how that's entered into the calculator. It's just super important to use those parentheses. And now we're just going to go graph, and this will be the standard viewing window, but it's also squared up. So if you do zoom 6, and then you'll see a graph, and you can do zoom 5, at least on the TI-84, and that'll just make sure your tick marks are spaced evenly apart. So this is what the graph looks like. It's just a line. Keep in mind though, even though that's what it looks like, there will be a point discontinuity at -3, which, lucky for us, is way off the graph. So if we're just graphing this on a nice viewing window of -10 to 10, we really actually don't have to worry about this. So we can just go ahead and keep drawing our line here, and if I want it to be a little more precise, I can see here that the slope is 3, and that's the slope of the asymptote, which actually is the graph itself. So I could go up 3, right 1, up 3, right 1, be a little more precise when graphing this thing. There it is right there. And keep in mind that down here, so we could even, I suppose we could even extend that a little bit, and you know, somewhere down here there's going to be a hole at -3. If we were talking about end behavior, remember that end behavior is simply as x approaches infinity, or to the right hand side, what does y do, or what does in this case f of x do? Well, f of x also goes to infinity. You can see that the graph keeps climbing and climbing and climbing. You can put any number in, any large number in for x, and you're going to get a large number out for y, and that value is going to keep climbing, or f of x. As x approaches -infinity, to the left hand side, this graph is continuing to go down, and it's going to go down to -infinity. We're going to go back, we're going to take a look at this domain and range now. It's possible to do the domain and range beforehand, but I like to kind of graph first just to make sure I really can see what's going on. So now I can use my algebra skills, I can use my graphing skills, and once it's in your graphing calculator, you can also make a table of values, and that will help you as well. For the domain, we have one value that doesn't work for this function, and that's -3. Everything else works, so we can go -infinity to -3, union -3 to infinity. Remember not to include -3 by utilizing your parentheses and not brackets. The range is going to be similar. There's only one value way down here that won't work. To figure this one out, we can use a table if we'd like, or if we think about like taking the limit as x approaches -3, that will give us this corresponding y value here. If we look at our work on the right hand side, we can see that x plus 3 would get canceled out. We'd be left with 3x minus 9, same as our slant asymptote. And we can use that to evaluate this the limit as x approaches -3. If we do that, we just need to substitute in -3 into the equation that we find when we cancel out the x plus 3, which is 3x minus 9. So when x is -3, that's -9 minus 9, which should be -18. So we don't want to include -18 in the range, so we can just go from -infinity to -18, union -18 to infinity. You can double check this in your calculator if you'd like, simply by going to the table set. The x value we're concerned with here is -3, and then make your delta table something small like 0.01 or 0.001. If you do that and go back to your table, we can see here that we're getting very, very close to -18. Now, actually at -3.001, the y value shouldn't be -18, as you see on the right-hand side there. That's actually a calculator error. It just gets so close to -18, the calculator doesn't know what to do, and it thinks it's -18. But actually, you can never, ever get out exactly -18, no matter what value of x you put into this function. And there you have it. We've got our graph. We've got some vertical, well, we don't have a vertical asymptote. We investigated it. There's definitely a point discontinuity. We found the domain and range. Asymptote, in this case, you could state that there's a slant asymptote, but it's not totally necessary. And here we've got our x and our y intercepts and our end behavior.